Academy's 1 week faculty development program on smart cities, organized by Civil Engineering Department, Government Engineering College, Bilaspur. I am overjoyed to take this opportunity to introduce our resource person of the session, Dr. G.D. Ramtekar, currently working as Professor, Civil Engineering Department, National Institute of Technology, Raipur. He obtained his PhD in Civil Engineering from IIT Bombay. His field of specialization is structural engineering. He has 29 years of teaching experience and also 1 year experience as scientific officer at Nuclear Power Corporation of India. His research work has been referred internationally in many research papers, PhD and MTech theses, as well as in a book. He has guided 7 PhD scholars. He earned University Gold Medal for securing first position in Bachelor of Engineering in Civil Engineering examination and nominated for Marquis Who's Who for a 2011 edition of Who's Who in the World. He completed structural design and supervision of 82-meter high monument Jaith Thumb at Virodpuri Dham, Raipur district, Chhattisgarh, as one of the tallest monuments in India. He is a member of Institution of Engineers, Indian Society for Technical Education, Indian Concrete Institute, Indian Building Congress, and Indian Geotechnical Society. He has authored many articles published by reputed international and national publishers, several papers and review articles in peer-reviewed journals. He will be discussing on topic seismic consideration for buildings and retrofitting techniques pertaining to smart cities. Without further ado, I welcome Dr. G.D. Ramtekar. Please, sir.
Thank you very much for your nice introduction. Now, I hope the audience is a mixed audience, and I will try my best to get the things related to seismic analysis and seismic considerations for their understanding. So let us start with actually first slide I have made specifically as the topic is. So I made it on smart city. So there was a great architect, Le Corbusier. Someone of you might have heard his name. Le Corbusier was the town planner of the first developed city, the Chandigarh. So when somebody asked him to define a building, then he told, building is a machine. Building is a machine we live in, where we live in. Means as machine is made for the comfort and convenience of the users, similarly a building should be made to take care of the comfort, convenience, safety and all the aesthetics of the individual who is living in. Exactly in a similar way, a city also can be defined. A smart city is a city. It is also like a machine where a community lives in. So for whole community, what are the necessary aspects required for a city that will form a smart city? Le Corbusier himself once told about that Chandigarh city that it has been planned as a human body. Human body has a head which is controlling everything as an administrative head. And then there are veins in our body, there are arteries and veins to, for flow of traffic flow as well as channelizing the waste flow and everything. So in the similar way, a city should also have various facets to take care of the needs of the occupants. In that way, I try to summarize the concept of a smart city, and I found these 8 blocks here. One of them you can see in this is smart building. A smart city must have a smart building. Now, what do you mean by smart building? Is definitely there are new gadgets have come up, so safety features, surveillance features, comfort features, that all should be there. But I will more focus on its safety of the building, because if building remains under the action of various forces, if it remains safe, then everything can be utilized. if it is not remaining safe, then nothing will be good for that. So smart building, out of that, I will consider one part of that. Then there is, in a smart building, there are various facets. Smart water management, there should be smart mobility for good traffic, no traffic delays should be there. We now see in most of the cities, we see the traffic congestion. So that should not happen in a city if we call a city as smart city. Flooding also takes place like that. Then it should be having smart energy efficient lighting, smart healthcare system where the availability of mobile vans and that ambulances, etc., and good hospital facilities should be available on phone call. Then smart energy, smart grid. Naturally, electricity is the prime thing in a city. Then reduction of travel. This is repeated. Then smart waste management system also should be there. Out of this, as I said, I will only focus on smart buildings, and that too, smart building where a building should be safe against various forces, and also it should be energy efficient. I will take up this smart building from the view of its safety against various natural and man-made forces. And what are those natural forces that and man-made forces that we consider in the design of a building? Mostly broadly, means there can be many more on that, but broadly they are divided into dead load, imposed load. It can be live load, it can be machine imposed load like this. So dead load, self weight of the member, and structural system. Then wind load, because wind blows and it has its own speed as a gust velocity. So that also puts force whenever some obstruction comes. We can also understand the effect of wind in a sense that when there is a huge wind blows, all those hoardings which looks to be very strong, they fell down. So the situation is that wind has a natural huge force, and that must be taken care of during design of a building. Then there is one very important force as seismic force. Though it occurs very means in years time, once in a year, but whenever it comes, it takes its attention, and building shatters because of that. So my concentration for today's presentation is again safety of building against forces, but that too particularly seismic forces, because once a building is designed safe against seismic conditions, then more or less we can understand that dead load, imposed load, wind load in most of the cases, unless it is very tall building, then all these forces can be incorporated within that seismic consideration, and the building may remain safe under the conditions of other kind of forces. So the thing that I will now go on will be based on the earthquake forces or seismic loading on the building, and how to make a building to remain safe against these forces. So I will take up the incidents that earlier also I have pointed out. It was about the Bhuj earthquake, and the date is not forgettable because it was the Republic Day, 52nd Republic Day of India, that is January 26, 2001. And the time was very early in the morning hours, when students were ready for their parades and all those things in Gujarat area at 8:46 a.m. in a Gujarat state, which is said to be one of the most developed state, means so far as infrastructure and people income point of view. An earthquake rocks the cities Ahmedabad, Bhuj, Anjor. And the statistics then says that over 20,000 people died, over 1,65,000 people injured, more than 20,000 people sustained serious injuries, more than 100 multi-storied building collapsed like play cards in Ahmedabad. This was happened for the first time. that a multi-storied building made with RCC structure, which is said to be a very good structural system and configured system, but such buildings collapsed due to that earthquake. This was the eye opener and a warning to the system. Overall, 1,87,000 Pakka houses collapsed and 5 lakh houses severely damaged. We can think the losses in terms of money. It is a huge money that is lost because of that earthquake. But it is more than that. We should not only think the losses in terms of money, but many things has happened, and the losses, irreparable losses, took place with the families. That somebody lost their family members, and that was irreparable. So we just not to think that the losses in terms of money, but in other social terms, that irreparable losses takes place if a building is not safe against such earthquake forces. So let us go into a bit of depth about blaming somebody who is responsible. It is not blaming, but it is thinking about what happened wrong and who should be held responsible logically. And if we see, then the two questions that comes to our mind is it the magnitude of the earthquake that has caused this devastation, or the magnitude of the negligence on part of civic authorities, architects, engineers, and builders? And here, actually, I would like to say the part of civic authorities comes, role of civic authorities, architects, engineers, builders comes very important in case of a smart city. If a city is made smart city, then all these authorities and the technocrats and architects should be very careful and very responsible, should behave responsibly. Now, about the earthquake, it is well known that an earthquake is a natural phenomenon. It can neither be predicted nor it can be prevented. Means one should be very clear about this, that it can neither be predicted nor it can be prevented. Then only thing is we can protect our building by suitable engineering provisions. The irony is that engineering equipment exists. Means there is not complete, but at least sufficient knowledge is available these days, which can be employed, then we can get, means this loss of life or property can be avoided due to earthquake. In Japan's or New Zealand, we often come across the huge earthquakes, but the loss of property and loss of life is in units. 1 people, 2 people, 3 people died, like that in places like Japan and that New Zealand. But here, if some comes, then the losses in thousands of people get their life. So enforcing that engineering equipment exists, that is why these losses are less in those cities, those areas of Japan and New Zealand and other countries. But the enforcing law doesn't. Actually, we require enforcing law where people who is constructing should be held responsible and should be monitored that all these provisions, earthquake provisions, are taken care of during the construction. So now going into that, is this slide changing? No. Yes, now it is coming. Let us have a glimpse of the construction practices which resulted in these calamities. So if we see that, then there comes the poor construction practices basically done. Though we know all those background science and understanding of how earthquake force affects the building and where should we take more care during construction, but it all goes in vain during construction. It is not taken care of that way, and this happens in this way. That this is a Tagore Part apartment building in Ahmedabad, G+4 story constructed in 1992. Here, this column failed. The buckling of reinforcement due to crushing and spalling of the concrete at the top of ground floor column. Basically, it is the ground floor, this stilt floor of a building, which is basically used for parking purposes and everything. That becomes most vulnerable. Under the action of forces, it is the horizontal force or the shear. This shear that hits maximum is on the this ground floor story at the top portion. And this particular column shows that the poor construction practice. Here there is we are not seeing the rings available here. So there is some my voice is clear or not? Hello?
Yes, sir.
Is it clear?
Yes, sir. Voice is clear, sir.
Yes.
There is some disturbance coming, I think. Okay. Okay. So what happens? Because of that concrete when gets out because of the vibration due to earthquake, when concrete gets out, these poor bars cannot to sustain the vertical load coming over it, and it buckles, and as soon as it buckles, the whole building gets collapsed, and it becomes a huge loss to the building and loss of life also. Poor quality of concrete in this zone of plastic formation. Here we must take much care during its construction. However, we see as in practice the least importance or least this care is given during this construction. Nobody cares. I found it is my personal experience. And this brittle concrete due to poor compaction and no confinement reinforcement, it held in this loss of the building. Then second thing is this is about a building which is Pranjal apartment in Ahmedabad. This is having a lift core. This is a lift core. All the four walls of the lift core are made using RCC concrete, reinforced cement concrete. And this is very strong so far as the lateral movement or lateral vibrations are concerned due to earthquake. So they themselves are very strong, and it can take huge amount of force in it due to earthquake. But the surrounding columns, if the surrounding columns are properly connected with this, all these columns could have been sealed. But as looks in this building that all the other columns were not properly connected with these shear walls. Not properly connected means the beam connecting all the other columns was not embedded, means the reinforcement was not well embedded in this lift core, and that is what happened during this vibration due to earthquake. The connection got failed, and all these other columns due to the earthquake forces collapsed. And in this way, there was the collapse of the building, and it resulted in 4 casualties. So no mechanism to transfer force to the lift core was there. No anchoring or continuity of slab and beam reinforcement to the wall of the core. Shear failure of columns led to the collapse as the core was not effective. This is how the mistake took place and resulted in 4 deaths. This is another poor construction practice where this corner column during an earthquake, the corner columns are subjected to the highest amount of forces because sometimes if it is center of as a seismic theory, if I talk about the seismic center of mass and center of rigidity, I will talk about it later. Because of that not matching in one point, the building starts, instead of vibration, along with the vibrations, it also starts twisting. To and fro twisting also takes place. That is called as torsional effect of the building. And because of all this, the corner columns are hugely affected because of the earthquake forces if the building is under twisting motion. What happened here is this particular location where I am putting my cursor. This particular location is a beam column joint. This is vertical is a column and this is a beam. Now, under the action of this earthquake forces, if failure is taking place, it may have taken place in the, as in the present case, it has taken place in the column portion. It may have taken place in the beam portion as well, provided a proper reinforcement detailing would have been done. But since in this present case, the column was weaker as compared to this beam, what happened due to this earthquake? Anyway, the failure was to take place and it took place in the column portion of the beam. Now, remember one thing, failure of column is a catastrophic. Failure of column means that whole structure will collapse. Whereas the failure of beam is a localized failure, only that beam would have failed, nothing else. Failure of that slab is even more confined. That is a small failure, localized failure. Failure of column is catastrophic, and that took place, and because of that, whole building collapsed. And actually, it violates the necessary condition or necessary regulation associated with seismic design, that your column should be strong and your beam should be weaker as compared to the column. Means saying meaning thereby that whenever it comes to the failure of the joint of a beam column joint, the failure should take place in the beam portion rather than in the column portion. Actually, here the failure took place in the column portion, and that is how collapse of the building took place. This is another example of a L-shaped building. There can be L-shaped, T-shaped, E-shaped, other various shapes of building. Now, as the earthquake is a vibration, when it vibrates in a particular direction, the stiffness of the system matters there. Stiffness has a very much say in the vibration characteristic of a building or of anything. Here we see that the vibration character or stiffness of this particular part is much different, and it is highly stiffer as compared to this T portion. And because of that, difference in the vibration characteristic of the two parts, when they are during construction connected together rigidly, it happened in the stress concentration at this location and failure of this part of the structure. So I will talk about this in the configuration of the earthquake resistant buildings. So this also is a kind of failure that takes place. Then another kind of a failure that takes place is, this is a G+4 story RCC framed structure constructed in two stages. Means first two story constructed once, then after few years the later two stories constructed. So what happened, because the later two story when constructed had not, means the column was not properly anchored, means the upper column was not properly anchored with the lower column, because probably there may be less amount of less length of the reinforcement available at that time, and people said okay ये चलता है, और इस प्रकार से in that way they constructed the whole structure having the weak joint between the older column and the new column that is coming up after the second story. During an earthquake actually tells everything, the mistakes that you have committed during your construction, everything is taken out and open, and without beyond question, it opens up your mistakes. That is what the quality of an earthquake is. So since there was no proper connection, the upper part collapsed because of that. Had this been a properly connected, probably this failure could not have taken place. This is another example of a short column. This actually is a normal case, as in normal case, is this? Yes. In normal case, what happens, there is a boundary wall, and actually, naturally, there is a gap between the floor and this wall, which is a boundary wall. But as soon we do it like this part of the column becomes a short column. From the point of view of any gravity load, like dead load, live load, imposed load, from that gravity point of view, even from the wind force point of view, this having a small or short column is a good thing. It is making the column stronger and stronger. But when it comes to earthquake, it is just opposite to that. When it comes to earthquake, it is An earthquake is something which vibrates the things. An earthquake is something which vibrates the deviation of one part of the column portion with the upper part. The magnitude of deviation that the earthquake wants will be given. अर्थक्वेक की मर्जी के हिसाब से उसको डेविएशन दिया जाता है, एंड एज मोर इज द डेविएशन और द sway of the column, so huge amount of force, as you might be the civil engineering student people may be knowing that it is what is the moment generated is, in case of a sinking of support of a fixed beam, we say it is 6 EI delta upon L square. So it is 6 EI delta upon L square kind of the moment generated. Now here L is small, so 6 EI delta is large upon smaller L square, and thus the magnitude becomes too large, and this too large magnitude is just because of the shortening of this column here. It is the short column effect, and hence in case of earthquake, short column effect is harmful. In case of wind force or gravity forces, short column is a stronger column. It is just opposite thing. So this short column effect compound wall resulted in crushing of the concrete and buckling of the bars. This is what happened. There is another example. This civil engineering people may be understanding that there is a concept of development length, that the reinforcement must be embedded within the concrete by that much amount to develop this particular quantity of stress within that reinforcing bars. Now, this is the classical example where the reinforcement was not properly embedded in the concrete and it just slipped away from that concrete. It has not taken any of the resistance or resisting forces, or nothing, no kind of stresses are generated within the bars, and it just pulled away from that system as if it was casted on a soil mass, something like that. So this has happened, and because of that failure to place of this particular column. This is another example we have learned. This is probably for the first time in India, a lesson has been learned that the staircase portion of any public building or any building, the staircase portion should be made separately, should be constructed separately with the other part of the building, and there must be a construction joint in between the two. The reason being that in case of a staircase, there is a inclined slab we cast, inclined kind of a shape, slabs. This makes the whole structural system of that staircase portion as very rigid. Means it is to and fro motion. It has a large frequency there, large stiffness there. Whereas the other part of the building has different stiffness factors. So what happens during this earthquake, when it tries to vibrate because of the earthquake, the frequency or the stiffness, because of the difference in the stiffnesses, it wants to vibrate in a different way, and the other part of the building wants to vibrate in a different way. And that made the collapse of the system. And naturally, when earthquake comes, during that moment of everybody goes towards the staircase to come down from the building. And this has happened here also. This was a girls' hostel where all the girls tried to come out through this staircase, and at the same time this staircase collapsed, and it has led to the death of some 9 girls there. This has given a new lesson that in the construction, particularly in earthquake area, prone area, this must be taken care of, that the staircases should be constructed separately as with the other part of the building, and a construction joint should be made there. This is another example. This is the example where the effect and proper connectivity of the shear wall. This is the lift core wall. Here, this portion is actually, there is a staircase here, and connected to that there is a lift core where there is a lift available. Since this lift core is made out of RCC and properly connected with other part of the building, all these columns were properly connected with the through these beams with the wall. What happened due to earthquake? The maximum force has been attracted by this lift core portion, and at the cost that this lift core failed. This lift core got these huge cracks, but all the other columns are saved because of that, and hence the building is saved from collapsing. So this is how the proper connectivity makes a difference and saves a building from collapse. This has also happened. This is another example where, as in the first example, I said there was no confinement given to the concrete, and as the vibration came, all the concrete from the column came out, and it was only single thin bars were there, and which naturally will buckle under the action of the gravity force, which is always there. Gravity force means dead load, self weight of the member, and all the imposed load, which always remains there, will act. And because of that action, as soon the concrete was come out, all these bars buckled and the collapse of the building took place. Here it is just opposite to that. What we see here, this column, sometimes we may see that this is a failure of the column, but it should not be looked like that. It is actually passing of the column, because this particular column is so properly confined by the reinforcement that even after this kind of a buckling and the vibration, the concrete inside of the column has not come out. And when it has not come out, the capacity of this particular column to take the vertical load still remains there. And because of that, the collapse of the whole building is saved. The building is saved from the collapse. And that is how the confinement of the concrete is of prime importance in case of earthquake resistant buildings. So we must take care, means if those civil engineering faculties will appreciate the things, that we do not give much of the importance with the rings in the columns or with the shear reinforcement in the beams. In case of beams, sometimes we calculate that what is the shear reinforcement required, but never we calculate what is the size and spacing of the rings required in a column. It is that neglected thing. But when it comes to earthquake, this becomes very important phenomena, that the rings should be so closely spaced that the spalling of the concrete from the inside concrete should not be there, and hence the building can be saved from collapse during an earthquake. This is what happened here in this figure. So in this way, if I want to ask that what kind of a behavior we want from a building, so it is this actually shown, that this kind of a behavior we want. This is the example of a twin tower, and at that 2001 when it happened, people have posted this kind of a animation. So basically we require a flexible structural system. Flexible means large deformation is there, still its capacity to take the vertical gravity load should remain there. If a building is that kind of a flexible, that large deformation is permitted, even then it does not lose its vertical load carrying capacity, then that kind of a building system is the most appropriate from earthquake point of view. Now with this all understanding, let us go into the heading of the topic, that required seismic consideration for a building, for buildings. Required seismic considerations for buildings. Now here an important note is there. Henry Degenkolb is he died some years back. Henry Degenkolb was a noted earthquake engineer, and he said, if we have a poor configuration to start with, all that an engineer can do is only provide a band-aid to improve the basically poor configuration as best as he can. Means he has given so much importance to the configuration of the building, means the layout plan, its vertical configuration, its its horizontal configuration. He has given so much importance to that, that if the configuration is poor, then not much can be done by the site engineer. A building of that poor configuration will definitely give a bad result, will behave very badly during an earthquake. Howsoever, attention and everything has been put in by the site engineer. Conversely, if we start with a good configuration and reasonable framing system, that is very important. The framing system means all these columns, lift core, everything is properly connected with one another or not. That kind of a framing system. So if conversely, if we start off with a good configuration and reasonable framing system, even the poor engineer cannot harm its ultimate performance too much. Means it is just contradictory to one another. If you are starting with good configuration and reasonable framing system, even if there is a very poor, means poor and no knowledgeable person is there at the site as an engineer, then also he cannot harm the structural system. Means the structure will perform in a good way, even with all this bad engineer who has constructed it. That is how is the contradictory system. These two sentences make it amply clear that the configuration and reasonable framing system are the essence of earthquake resistant building. So now we are going into that configuration. So seismic considerations during planning. There are, now I will talk about plan configurations, means how the system should be there in plan. So you just see all these kinds of a building that we come across. This is a too tall building with slender cross section. Means the cross section is very small, but height of the building is too large. This is another building which is too long. Means the length as compared to other two dimensions is very small, is too large. And this is a building which has too large in plan. Means its length and width is too large. All these things, too large, too tall, too long, is not good from the consideration of earthquake resistant building. What happens whenever there is earthquake hitting? Say for example, if it is, this building is too long. Now when this is a too long building, earthquake actually is waves. It comes through the waves in the soil strata, and as the waves it has certain wavelength and all those phenomena are associated with the vibrations. Now naturally, the way this particular part is being vibrated because of the earthquake, this part may not be having the same kind of vibration as vibrated by the earthquake. This may have been vibrated in a different way with certain lag in the vibration. Means first this part may be vibrated and then the vibration gone into this location and vibrating this. When this was vibrating, this this came into standstill condition, and this is how the whole building is not simultaneously vibrating. Had this whole building is simultaneously vibrating, then the behavior would have been more proper. Everything is vibrating in the same way and there is no distressing or additional stresses coming in any part of the building. But if one part is vibrating and other is standstill, or other is vibrating, first part is standstill, then naturally it creates a concentration of stresses at locations, and then it leads to the failure of the structure. So also happens with this large plan area, and in this area there is a large deformation possible. Because if it is a too tall a building, during an earthquake, when it is earthquake is vibrating from the bottom, the top portion is not knowing about anything that is happening to the earth, and it remains standstill, and this bottom portion goes away too large. And under that condition, what happens? The gravity load resisting system of this whole building collapses. Means with that large deformation of a column, the column is unable to take that gravity load which always is coming there. and which always is coming, but now the system is not perfectly vertical, but it is inclined somewhere, and this creates additional movements, and due to that the building collapses. So anything too much, too large, too tall, or too long is not good from the earthquake point of view. So this is how, this is a long building, and the Bhuj too long, and it, this one part of the building collapsed because of this consideration that it is too long a building. What should we do in case, naturally a big building is the need of the hour. So large, too long, too large building actually are coming. So under that conditions, can we give a separation joint or construction joint at various locations, so that when this is vibrating, this whole is vibrating, and nothing to worry about whether this part is vibrating or not, or this part is vibrating, or if this is vibrating, let it remain vibrating. So in that case, I can say that this part as a whole is vibrating, this part as a whole is vibrating, this part as a whole is vibrating. And since there is no connection in between, its vibration is not affecting this vibration, and its vibration is not affecting this vibration. Each of them are vibrating in their own way, and their capability, and this additional stresses because of this, some part is vibrating and some part is not vibrating. In that way, it is different lagging of the vibration, which creates the additional stresses will not happen there. So this kind of a construction joint can be provided in that situation if it is a too large. If it is a too large building, then this kind of a construction joint can make the things happen well, or they behave well under earthquake. Then there is another kind of a building, that many buildings we see having L-shaped building, T-shaped building, cross or I-shaped or E-shaped building. Many such shaped buildings we see in government sector, in private sector, in public sectors as well. Now, one example I have already given, that there was a T-shaped building where the T portion collapsed during the earthquake. Actually, what happens? We do not know the direction of vibration that will occur due to an earthquake. We do not know. Now, say for example, this is a L-shaped building. This L-shaped building is there, and if the vibration is taking place as my cursor is moving, this is the direction of vibration. So this is the direction of vibration. Naturally, under this condition, this particular part has the different stiffness and large stiffness as compared to this portion, because this is smaller in width and its stiffness is much smaller as compared to the stiffness of this portion under this condition of this kind of a vibration. If this is the vibration, if the this kind of the vibration is taking place, then this becomes too stiffer as compared to this portion. So that is how the stiffness change is there in the building, and under the earthquake effect, this is sudden change in the stiffness. Sudden change in the stiffness makes the difference. And because of this sudden change in stiffnesses, results in the concentration of stresses at such location. It is called as reentrant corners. At this reentrant corners of the building, at these corners of the building, there is a huge amount of force generated because of the sudden change in the vibration characteristics or the stiffness of the system. This leads to the failure of this joint, and as soon the joint is failed, the column collapses and the part of the building collapses due to this earthquake. This is what happened because of the reentrant corner force. So any building, if made like this L-shaped, T-shaped, cross-shaped or H-shaped, should be given due consideration during its construction. That I will talk a bit later. This is what is the situation, as I already explained, that happens, and this portion becomes, during the motion, this portion becomes the location of the stress concentration, and tearing of the structural portion takes place at this location. Had this been made like this, means there is a construction joint given between them, then during any axis of the motion, if our vibration is vibrating along x-axis, no problem. This will vibrate in its own way. This will vibrate in its own way. It has different stiffness. It has different stiffness. No problem. because it has to vibrate in its own way as a whole. This has to vibrate in its own way as a whole, and there is no, as there is no connection in between, there is no question of stress concentration. And because of this, the building can be properly designed, economically designed, as well as more guarantee can be associated. There is as such no guarantee can be given against the earthquake, but still a percentage of guarantee or percentage of assurance may be given more for such a building that it will not collapse, as compared to this kind of a building where there is a monolithic construction like this. So a building should be constructed in that way when the building is having re-entrant corner. Sometimes what happens, as this is the re-entrant corner, then this portion, as I said, it is this corner basically severely affected and subjected to stress concentration and the failure. So this corner portion must be given due attention, and the construction of this portion, the beams and columns of this portion should be designed accordingly so that the failure due to this stress concentration also do not take place. Either you construct in that way, naturally that kind of a construction will be a costlier construction as compared to normal. I hope I am audible. Hello?
Yes, sir. Audible, sir.
Okay, other thing that can be done, this is a C-shaped building having these re-entrant corners at this location. What people can do is, there is a connecting beams given at this location. If your architectural system is not affecting, the architecture is not affecting, then it can be given this connection, and hence this is building as a whole is connected and vibrating in a way. So this is one way of remedial measures for such building can be proposed. This is one such example of re-entrant corner failure, that during an earthquake, all this part and that part remained, but this collapse. Now, other way of this re-entrant corner can be done is by splaying of the system. There should not be sharp corner here, rather it should be splayed like this. If it is done so, then the change in the stiffness of the two portions is gradual, not abrupt. As in this case, it is abrupt change in the stiffness characteristics. Here, the change is gradual, and under this gradual change, naturally, its behavior will be much better as compared to this behavior, and the system is more stronger here also, and hence the joint failure may not take place. This is how it is done here also. Then these are the coded provisions as IS 13920, ductile detailing provision. There, these kinds of figures are also given. If your building is L-shaped, provide a construction joint like this. If it is T-shaped, Y-shaped, E-shaped, this kind of a construction joints can be provided. Okay. So now let us come to another concept of the building, that when building vibrates. So as a vibration theory, we understand that vibration means the mass of the building is vibrating, and as the mass is vibrating, means mass is under acceleration, to and fro acceleration and changing acceleration. And when mass is under acceleration, it results into inertia force. Now, the inertia force of the whole body, if taken, say for example, this particular building is vibrating in this way, then the center of that mass, if taken as the resultant location, then this is the center of mass, and this is the mass in which it is vibrating. What is resisting, what is bringing it back, means if a system is taken away, means if a column, one portion is kept here and other portion is vibrated, then what is that it brings it back? It is the rigidity of the system or stiffness of the system that brings it back. So that applies its own resisting force or to bring it back, that kind of a force. That force, naturally, the CG of that force or the resultant of that force is wherever it is acting is termed as center of rigidity. Now, if the structural system is such like this, it looks in plan very symmetrical. If the system is that symmetric, then center of mass and center of rigidity are at the same line. And if a structural system vibrates like this, then center of mass and center of rigidity are complementing each other. And that is how no additional stresses, naturally because of this vibration, stresses are coming in the columns and beams portion, but additional stresses are not coming. As I will show this is one of the figure where if this kind of a building is there, though in plan it looks symmetrical, but what happened, in a construction there was a shear wall arrangement made here, but no shear wall in any portion, and that way rigidity point of view, this is much stiffer a system, hence center of rigidity or action of elastic force will be more concentrated at this location. However, the mass is distributed across the whole building and its center of mass may be at the center location of the building. In this case, this is the action of inertia force and this is the action of elastic force. And when there is a difference in that location of the action of inertia force and elastic force, what it will lead to is a generation of a couple. And this couple basically tries to twist the building. So twisting effect or torsional effect is additional thing that is going to come up because of this asymmetry of the system, that elastic force concentration in the center of rigidity is not coinciding with the center of mass, and hence it leads to the extra twisting of the system that is creating extra stresses in the column portion and particularly in the column portions and leading to the failure of the structure. One such example I have given earlier, as because of this twisting system that building collapsed. Had this been made like this, that this is a building which looks symmetric in plan and naturally its center of mass will pass from this. However, the arrangement of shear walls is made such that its center of rigidity is also at the same axis. It is in the symmetric location. And under this condition, if it is vibrating, there is no additional resultant torsion taking place, and hence this building is behaving much better as compared to the behavior of this building, which is not where the inertia and elastic forces are not in the same line. So this is how the building, when designed, during design of the building, all these things must be taken care of. This is another example. This building, now as I said earlier also, that we do not know which will be the direction of earthquake motion. Means earthquake can take the building moving like this in this direction, it can take the moving in this direction. Now in this particular example, it seems that earthquake is made to vibrate in this direction. This is the direction of vibration of the building. Now here there is a shear wall here. Naturally, the center of rigidity is associated with this location. However, since this looks symmetric in plan, the center of mass is somewhere at this location. So center of mass is acting here, and means inertia force is acting here, elastic force is acting here, and thus causing twisting of the building, and this may lead to high stresses in this corner column. Now the same building, if the same building is vibrating in this direction, we do not know which one will be the direction of vibration. If it is vibrating in this direction, then fortunately, though the direction of the location of inertia force will be here, and the location of this elastic force will also be in the same line, and hence there will not be any twisting in this building under this kind of a vibration. But this building makes it sense that under a particular kind of vibration it is symmetric and not causing the twisting, but under the other kind of vibration it is causing twisting. So this kind of construction should not be done, because we do not know the direction of earthquake when it hit the area. What will be the direction of earthquake? This is how it takes place as the torsional effect, and the corner columns are severely affected because of that. Had this shear wall be made like this, naturally it leads to the symmetric positioning of the shear walls, and center of mass and center of rigidity will remain in the same location under any kind of a vibration, whether it is along x-axis or y-axis or along other axis as well. Then this kind of a configuration is a better configuration so far as earthquake behavior is concerned. This is what I have talked about the plan configurations. Now let me talk about the vertical configuration. When we talk about the vertical configurations, there are this kind of a building that we come across, that a building having large plan area and then a smaller plan goes to heights. This is another kind of a with setbacks. This is a typical kind of a construction where the bottom portion is having less plan area, whereas the top portion is having large plan area. These are another common kind of a building that we see as a multi-story building, where the bottom columns are unfilled. There is no wall infill here, whereas the upper portions are filled up with the walls. So this is infilled wall portion, and this is a bare column portion. It is a soft story. It is called as soft story. This kind of a construction. This is too large length, means height of the column here, and rest of the columns are having different unusually tall building like this. These are the various kinds of vertical configurations we may come across in building systems. Now, there are other configurations also, that if it is a hilly area, this kind of a construction of building we usually see. In case of hilly area, that this particular column is like this, and this is, so here this column is large, long column, whereas these columns are short column to some extent. This is one kind of a structural system in ground, though not advisable, but it happens. This is a peculiar type of a construction when the greed of the builder actually says that as per Nagar Nigam or the municipal corporation guidelines, I have to take this much part from the ground, but upper part I can go. This kind of a system happened in many places. Here what happened, during an earthquake or otherwise also, this particular column, which is a floating column, actually is putting its force like this. But the way this load is to be transferring to the ground below is by virtue of giving a bending here, huge bending here, then huge bending here, and then only it will pass through this. This basically leads to the failure of the structural system. Here there is a stress concentration, and basically this stress concentration is also at this location, and this is called as load path, and this kind of a load path should not be there. Here in this kind of a construction system, the rigidity of this top portion is too large because it is infilled wall, whereas the rigidity of this bottom portion is smaller. It is the summation of the stiffnesses of all these columns, whereas this particular portion has summation of the stiffness of all the columns along with the stiffnesses of the brick walls. And when it comes to brick wall, if it is the length of the wall, so perpendicular means along that length of the wall, it is too stiff. So that high stiffness is associated with the stiffness of the column, making this top portion too much stiffer, and the bottom portion as compared to that too small stiffer. And this too small stiffer portion as compared with this too stiff portion of the upper story makes this story as a soft story. What we mean by soft story is whole of the deviation or displacement that takes place because of the earthquakes will be concentrated only in this small part. Whole of the sway will be concentrated, will take place only in this part, and the upper part will remain straight. That leads to high stresses in this location of the column and leading to failure of the structural system. So open ground story building is the same thing. As I explained here, this is how is the schematic diagram showing what happens if the upper portion is filled up with walls and bottom portion is a bare columns there. Now, due to earthquake, this has to vibrate. But instead of this kind of a smooth vibration, means a smooth deviation, what happens is 100% all the deviation takes place in this portion, and then rest of the portion remains straight. So this particular portion is too highly stressed and leading to failure of the system. This is called as soft story. This is what happened in the soft story cases of a building. This is another example of that case of soft story, that these are the two buildings constructed in as the 4-story building with soft story. Because of earthquake, this is nothing happened to this. However, this building collapsed and it is now 3-story. It looks out of this is 4-story building. This remains only 3-story. 1 story is gone. This is how the soft story has affected it. This is another example of this infill wall. What can be done now? This is a remedy if of the soft story, particularly in the parking stilt floor. You provide, if you can provide walls. You should provide walls like this. Or if walls are unable to be provided, then at some location this shear wall should be provided, so that stiffness of this bottom portion or the stilt portion also matches with the stiffness of the upper stories. If it is matching, means it is in consideration with the upper story, then that kind of a soft story concept will not come up, and hence the failure of that bottom story will not take place. The sway or lateral displacement will be uniformly distributed across the height of the building, and hence the bottom portion only will not be subjected to too large stresses. Rather, it will be subjected to less amount of stresses, and that less amount of stress will be distributed across the length, and the collapse of the building can be saved. This is what is the remedial way. The other remedial way is, if this kind of a construction you need to do, then this bottom stilt portion should be made with heavier column section, so that it is stiffer. So far as this column is concerned, as compared to the upper column, the stiffness is too large, and the summation of all the stiffnesses is making equivalent or more or less comparable the stiffnesses of this infilled system. If it is so, then also the failure of this or soft story kind of a thing can be avoided, and the building can be saved from collapse. Then, as I already pointed out, the short column effect in one of the example, this is a long column, this is this short column. Now, with earthquake, it should be understood in this sense that earthquake is a displacement, not a force. Force is generated by virtue of its inertia, by virtue of its mass being accelerated. When mass is accelerated, P is equal to mf as per the Newton's law, force is generated. That's okay. But if actually it is giving a to and fro displacement to the building, and if delta is the displacement for this column, which is a large column, long column, and the same delta is displacement given to this short column, the amount of force generated as the say moment 6 EI delta upon L square here and 6 EI delta upon L square here, if this length L, say this length is 2 times the length of this, then I can say the force generated here is 4 times higher as compared to the force here, because it is 6 EI delta upon L square. So the half will be 4 times greater. This will be 4 times greater as the force. Similarly, shear force will be 12 EI by L cube. So means it is 8 times subjected to higher shear than this. 2 into 2 into 2. So this is how is the situation, and short column effect comes in case of our this earthquake forces. This is how because of the short column effect, there was wall here and there was wall here. In this portion, because of the wind, there was no wall, and this became actually a short column and this kind of a cross section. This cross failure or cross cracks represent that it was subjected to vibration, because it is the vibration that brings out the tension in cross pattern. Because once it is vibrated in this direction, there will be tension in perpendicular direction. Then it is vibrating in the other direction, there will be direction of tension will be in other plane, and thus it is a cross type of a failure that takes place in the building. These are the examples of in slope this becomes a short column. Then it is advisable that all the footing should be developed or could be constructed in one same level, so that this short column kind of a effect can be avoided. This is another example of weak. Now we have to compare between strong column weak beam or weak column strong beam. It is a comparative study, and in this comparative study, naturally, as I said earlier also, that the collapse of a column is catastrophic and whole building collapses, and whereas the collapse of a or failure of a beam is a localized failure. Naturally, during an earthquake, we would like to have, if at all it has, then to have a localized failure rather than a catastrophic or complete failure of the system. And with that philosophy, we always would like to have a strong column and weak beam comparatively, that kind of a construction system, rather than a weak column and a strong beam system, as sometimes happens. So this is the concept of weak beam and strong column system. What about setbacks? Naturally, setbacks will lead to different stiffnesses, and then there is variety in the vibration. Because sometimes we see that it is the earthquake that has come and vibrated, but when earthquake comes and goes away, still the building starts building keep on vibrating. It is similar that if I have a rod, steel rod, and at one end I have kept it, and at the other end I am pulling, I am putting a hammer on that. As soon I will hammer it and I will leave away the hammer, still the building or the rod will be vibrating for some time. The same thing happens with the building. Earthquake comes and goes away in a fraction of minutes, means hardly 10 seconds, 20 seconds, 30 seconds, the earthquake has come and gone. But the building keeps on vibrating for minutes, because once the energy is imparted, now the building is vibrating, and in that case of vibration, this part is vibrating in a different way, wants to vibrate in a different way as compared to this portion, because of the change in their stiffnesses. And because of this, what happens, there is a stress concentration taking place at this location of reentrant location, leading to collapse of this part of the building. And that is what happens. And if we want to avoid them, then the building should be constructed in this way. There are many limitations. What I want to highlight here is, when it comes to earthquake, there are many limitations that comes in our way of designing. It is a tedious way of designing the earthquake system. So there must be a good collaboration with the architect and structure. Architect should also understand the structural system or behavior under earthquake, and then only a proper system, safe, more or less safe system, can be evolved as the design of a structural system. So these are various recommendations that building regular in plan and in elevation without reentrant corners and discontinuities in transferring vertical load to the ground display good seismic behavior. ये समझने वाली बात है कि ऐसा हो बहुत अच्छा है. Concrete shear walls should span whole distance between adjacent columns. In this way, both strength and ductility of the structural system are enhanced whenever we are providing the shear wall. All structural elements forming the structure, including foundations, should be well interconnected to build a monolithic structure, high redundancy. So here it is advisable that even though they are the isolated column system, if possible, if they are connected together at the foundation level, it is good from the earthquake behavior point of view. Flat slab system, which is nowadays much popular. Flat slab system means without beams. Basically, it is not needed to write another thing. Flat slab system without beam should be avoided, because when there is no rigid system, the behavior of flat slab supported on the column is not very well understood, and it is not good so far as the earthquake forces are concerned. Short column resulting from mezzanine or steep wall below window should be avoided. If it is necessary, proper design should be done. There are some way to avoid the bad things. Large discontinuities in the infill system, such as open ground story, should be avoided. Structure should be composed of strong column and weak beams. It is advisable for structural system to include a second line of defense formed by ductile frames. Now, what is the ductile frame? We will talk a bit later. But the concept of earthquake resistant design, the huge amount of earthquake force is actually imparted to a building, and if we like to design it as a elastic building, then nothing less than a pyramid of mist will be constructed. Means a huge 100-meter by 100-meter structure for a 10 feet by 10 feet room. It is that kind of a structural system will come out if we require a building to behave elastically during earthquake. We cannot afford that. And under that situation, a ductile system comes to our defense. That a system which is ductile enough to reduce the effect of the forces of earthquake by virtue of its displacement and micro cracks that is generated. That is what actually is the concept of ductile framing. Footing should be interconnected either by a made foundation or a grid foundation. Beams with connecting beams. All footing should be rest on the same horizontal level. This is one of the challenge in hilly area. May not be possible, but from earthquake behavior point of view is a necessity. Only one foundation type should be used in the whole structure. Then let us talk about important points for better seismic resistant structural system. Heavy buildings attract more earthquake forces, because as the mass is higher, with the mass multiplying to the acceleration, making it a huge inertia force. So naturally, a heavy building attracts more earthquake forces than the lightweight. Try to avoid heavy weight, particularly in the upper floor. If it is in the upper floor, there is huge force applied at the top portion, whereas it is supported at the bottom foundation level. So it is creating too large a movement. So as we go on higher and higher in the building, if possibly the building is becoming lighter and lighter in the upper story, is good for the health of the building under earthquake. The otherwise, if it takes place, people are they are actually fascinating about the having a swimming pool at the top of my building. This is too much dangerous during an earthquake. An increase of stiffness for the sake of reduction of deflection and vibration results in large lateral inertia forces. With steeper system, we should make a stronger also. Stiffness and strongness are two different things. Stiffness is something related with its EI, so that deflection is lesser or something like that. But strongness is the whatever forces it is subjected, and as per that, the reinforcement for RCC is available or not. A ductile moment resisting space frame may be preferable to a braced frame or bearing wall structure, since it generates smaller seismic forces. However, it may endure large deflections under severe earthquake because of the flexible system. However, even after that, a ductile system is the most preferable system. Hello? The ductile system is most preferable system. Steep building resists deflection, thus reduces damage to non-structural components, particularly in moderate earthquakes, but do require more structural. The mass and stiffness of building should be uniformly distributed to prevent torsion. Abrupt changes in structure with sudden changes of stiffness causes stress concentration, resulting in potential failure. These are all about our structural configuration that is required. What kind of a configuration is good for earthquake system and what is not good for earthquake system so far as its plan configuration or vertical configuration is concerned, or center of mass and center of rigidity. All those things I have tried to tell you. Now coming when about the seismic retrofitting means the old buildings are already there. It is not that a smart city is coming up, then all the building will be dismantled and new building with new seismic consideration will be constructed. It is not like this. There is always necessity that old buildings which change in its views or which change in its earthquake zoning and all those things needs retrofitting. So this is the topic of now I am presenting, that seismic retrofitting. So at this stage, we must understand the difference between these various terms which are loosely used. One is repair, maintenance, restoration, strengthening, retrofitting. These are the 5 terms that we generally use as synonymous terms. So this is one of the diagram which clearly make the distinction between all these things. That a building when just constructed means it is the 0-day life. 0-day life has a certain strength here, but as the life as it is aging, then natural deterioration or natural deterioration in its strength taking place. If the building is properly maintained, every year we are doing all those small cracks which are coming, repairing and all those things, then this dotted may be the curve it will follow with time. If it is not properly maintained with time, means seepage हो रहा है तो होने दो कोई बात नहीं, क्रेक आ रहा है तो आने दो कोई बात नहीं, मेरे को थोड़ी रहना है, इस टाइप से अगर कॉन्सेप्ट से लेंगे तो it is the second graph that it is taking place, it is losing its strength too fast, and sometimes during that its life, if any damage has occurred, drastically reduces the strength and it goes down. Now this is how is the behavior of a structural system that takes place with time. Now if I do certain maintenance of the building just to restore its this dotted line, this will be termed as repair. मतलब एज के साथ में उसकी स्ट्रेंथ जो कम होने वाली है मेंटेनेंस पोर्शन में, वो तो कम रहेगी, बट अनमेंटेन्ड एजिंग विदाउट मेंटेनेंस को मेंटेनेंस के लेवल तक लाना इज कॉल्ड एज रिपेयर. But from this level, bringing it back to its 0-day strength means at the first day, what was its strength? If that strength we are bringing by certain activities, that will be termed as restoration of the building. Now, if the building is constructed and probably I do not know what is the use going to be. So at that time, say if it is constructed as a residential building and at later stage, at certain age, it is decided that let it be a library, then naturally the forces that are coming due to library is much higher as compared to that due to residential building. So here I require strengthening of the building. So from this portion I will restore it, and something structurally I will do to strengthen it to the level required for its new use as a library. This is called as strengthening of the structure. Now sometimes happens that a building is constructed when the earthquake zoning was there, and this say for example this Raipur, Bilaspur or this area was coming in zone 1, and the least amount of seismic force was required to be considered, and that was also not mandatory. Now it is a higher amount of force and mandatory as well. So likewise in Jabalpur was in zone 1 earlier, but suddenly when this earthquake took place, it is brought to zone 3, means a higher amount of seismic force is required to be considered. Now what to do with the old building? Then the building needs to be not only the restoration but also strengthening so far as the seismic behavior is concerned. And this seismic behavior strengthening will be termed as retrofitting of the system. So basically, we are actually talking about the seismic retrofitting in this sense. So as per the definition, it is the modification of existing structures to make them more resistant to seismic activities, ground motion or soil failure due to earthquake. The retrofit techniques are also applicable for other natural hazards such as cyclones, severe winds and thunderstorms. If this is changing, accordingly also it needs to be done. The seismic retrofitting gives improvement to an existing building and increasing the global capacity of the building. Now there are various ways in which the seismic retrofitting, either you say seismic retrofitting in one sense or you say strengthening of the building in other sense. In both the senses, there are various ways to do that. And they are broadly classified like section enlargement, external steel plate bonding, post tensioning of the system, ferro cement laminates, and use of fiber reinforced polymer composite. I have purposefully given it a different color to highlight this because this is most promising these days. This use of fiber reinforced polymer composite is most promising way of seismic retrofitting and strengthening of the structural system. And at many places you may have seen that use of fiber reinforced polymer composite is done for seismic retrofitting and strengthening. So the first part, that is section enlargement, it is done like this. This is a schematic diagram of a T-beam. This is the slab and this is the beam. Now say I want to enhance the capacity of this beam. Now naturally this beam is subjected to bending moments and shear forces. Now bending moment, actually for taking the tension due to bending moment, these reinforcements are already provided in the building, in the beam. And now as part of the strengthening or retrofitting, I need more capacity of moment resistance of the system, and thus needing extra bars to be imparted. Now imparting extra bar is one thing, but making them monolithic to behave with the old beam is another thing. And our purpose as a structural engineer is that they should be made monolithic with the old structure so that the behavior of the whole structural system is there with the enhanced capacity of moment resistance and shear resistance. How to do that? Then there are holes can be dug here, and with some chemical this reinforcement is put here, and there this tension reinforcements are provided, and they are properly concreted here, so that by chipping the old concrete of the structure and making this connection of the new concrete monolithic with the old concrete, so that under this condition these new added bars also come into play to take the resistance of the moment of resistance. Similarly, these vertical bars to some extent are working as a shear enhancer, shear capacity enhancer. This is how it can be done. So increasing the load carrying capacity, increasing the stiffnesses of the advantages. However, increase in the concrete member size obtained after the jacketing. Here this size is largely increased, and sometimes it does not look aesthetically good. So that is the problem with this kind of a work, section enlargement. This is another with less amount of section enlargement is there, external plate bonding. Now, as we know, steel is much stronger as compared to the RCC work. Now, any steel plate, if it is if somehow if it is this plate can be joined with the concrete, then it will act in the behavior of the beam. So epoxy adhesives are there which when pasted on this old concrete and a plate can be pasted, then this plate will monolithically act along with this beam. And naturally, if a plate is pasted here, in some as a strength of material problem, people have used how the moment carrying capacity increases with the flitted beam kind of a thing. Everybody has studied in strength of material. that kind of a thing happens and the moment carrying capacity can be increased. It also increases the shear capacity. Now these holes are given sometimes to give more proper shear connection with the old building, old structure beam. That can also be done. So this is another way of external plate bonding. Then sometimes, mostly in case of a bridge system, this can be done, that this is a girder and needs to be its capacity or moment carrying capacity and shear carrying capacity to be increased. I am particularly talking about this post tensioning in respect of its moment carrying capacity. So outer surface, there are these ducts are provided on these existing beams, and it is connected with this shear rings also. And through this duct, if I put the pre-stressing tendon and using the jack, if the pre-stressing can be imparted, then the whole system will be pre-stressed, and thus enhancement in the capacity of the existing structure can be done. This is how post-tensioning work can also be done. In small cases, sometimes, as you see that if there is a seepage in this slabs, so what people do is one inch or 2.5 centimeter layer of concreting is done like that. So that is not actually enhancing the strength. Okay, it may be possible that seepage portion can be is reduced, but if it is done with is wire mesh, then some strength enhancement also is possible. So if that is done, then it is called as ferro cement laminates. So ferro cement work is also done for smaller work to enhance the capacity of the. But the most promising one is this fiber reinforced polymer composites. Fiber reinforced polymer composite, as this figure shows, is something, it is kind of a fabric. जैसे हम अपना पैंट शर्ट खरीदने जाते हैं दुकान में और हमारे पैंट शर्ट जिसे एक रॉड के आसपास लपेटे हुए रहते हैं या फोल्ड किए हुए रहते हैं, exactly in that way this fiber reinforced polymer composites are wrapped like this. So this is such a kind of a flexible material, can be taken from one place to the other place easily. That is what. But with that less of its self weight, it's very lightweight. In one way, having the lightweight is a much good thing from transportation point of view. But it is not only that as the benefit. It has very high strength. It has something 5 times, not even more than that. 5 more than that times of high strength this material is having. It is corrosion resistant also, and it is very versatile material, and it can be, the usability of this material is very easy, and it does not change the shape and size of the section already available. Means जो section है उसके section में millimeters का कुछ अंतर आ जाएगा. If section is 200, say 200 millimeter by 400 millimeter beam is there, and I am retrofitting it, hardly it will become 203 millimeter to 405 millimeter. That's all. इससे ज्यादा कुछ होने वाला नहीं. 2 millimeter on this side or that side, 5 millimeter on the bottom side. That is what is the size enhancement. So with this least size enhancement, it is giving too large capacity enhancement. That is why it is the most versatile material being proposed as a retrofitting material. The only thing it has, actually, it is not having that kind of a ductility as actually is required from seismic point of view. That is correct. That our steel rods are having much percentage elongation capacity, and that kind of a percentage elongation capacity is not there with this material. That is correct. But enhancement of strength is quite good with this kind of a material. So this is one chart that is giving a comparative study between steel reinforcing bar and glass FRP and carbon FRP. Mostly it is the carbon fiber reinforced polymer that is being used. And here you just see the comparison. There is no yield strength comparison because it doesn't have a yield strength. It is the ultimate strength. So its tensile ultimate strength is say for example 100. It has something around 400. Means 4 times higher as the strength it offers. And modulus of elasticity is also comparable. It is 20,000, it is 29,000. That's good. Means it is a comparable. Means it is not very much less as compared to the steel. It is comparable modulus of elasticity means large deformation के बाद में stress आएगी ऐसा भी नहीं है. जितने deformation से steel में stress आ जाएगी उतने ही deformation से इसमें भी stress आ जाएगी. At least workable stress I will achieve with the kind of straining of that steel. Same straining will give a sufficient amount of stresses within this carbon member. Percentage elongation point of view, it is something more than 10%. It is hardly 1 to 2%. That is one thing associated with. So far as the weight is concerned, it is 490 and it is 100. Meaning it is 5 times heavier. Steel bars are 5 times heavier, and this is 4 times of stronger. In this way, 5 into 4 is 20 times better. I can say a carbon FRP is 20 times better than a steel reinforcing bar. That is what is the benefit of this FRP. So how to apply this? Temperature. Now you should understand while its application, the caution must be taken. Temperature, relative humidity, and surface moisture at the time of installation can affect the performance of FRP system. I hope things are clear. I am making the things clear. Hello. Okay. So the conditions to be observed before and during installation, a heat source can be used to rise the surface temperature during installation. Adhesive should not be applied to damp or wet surfaces. These precautions we must take. Method is the surface must be cleaned and roughened to ensure a good bond. An adhesive layer of epoxy is applied to the structure prepared surface and FRP strips are put in place over the epoxy. Now clamps are commonly used to hold the plates in place while the epoxy cures. So the curing time of epoxy is something 2 hours. So for 2 hours, some system we require to imply that whatever FRP fiber that I have laid over the epoxy should remain there with some pressure so that it gets completely fixed at the location. Another layer of epoxy is applied over the fabric to saturate the fibers and create a continuous composite material. Now this is how is the application. If for flexural strength means bending moment capacity को बढ़ाना है, moment resisting capacity को बढ़ाना है, so naturally its application will be in tension side. So if this is a beam, this is a kind of a beam with tension side at the bottom, I will put this FRP at this location. I can also put at this location as well to enhance its capacity so far as the bending resistance is concerned. This is how I can put the FRP over the beams, RCC beam. If I want to enhance the shear capacity, then this kind of arrangement I require, so that, and this kind of a pasting of the FRP over the beam needed so that its shear strengthening, shear resistance can be enhanced. When I require confinement, actually it is the confinement of concrete that is needed in case of a column. If it is confined, then it is too hugely strengthened. एक concrete section की strength बहुत ज़्यादा होती है अगर वो confined हो. It is just as an example I am giving. Say for example, I have a heap of sand. I have a heap of sand and just I am sitting over its top. As soon I will sit, I will just be the deflection will be there by large amount. Means I will come down by some amount. But if the same sand is there in a container, एक ड्रम में आपने sand भर दिया है और अब आप उसके ऊपर बैठ रहे हैं, do you think that kind of a displacement will take place? It is not. Even though it is the same sand, only the confinement is changed. Because of this confinement, there is no that kind of, means it has a large capacity to take the load. Something that kind of thing happens, and on this confinement is very well done by the FRPC across around the columns. Now, these are the suggestive retrofitting schemes for various structural elements like footings, columns, beams, and slabs. So these are the actually primary elements of our building system. So what way can we retrofit this kind of a system? So the first example is that of the column. Now, if the first example is that of footing. Now, in terms of footing, footing is at the interface of a structural member RCC column and soil. In between them, the structural system that comes is this footing. Now, there can be two types of retrofitting required. One is the soil is strong enough. There is no problem in the soil. So whatever is the size of footing that is available is sufficient. But the structural system of that footing is not sufficient so far as the bending moment of shear force that is coming because of the enhanced loading on the structure. So what I need basically is the enhancement in this capacity of the structural system of the footing, not increasing the size. If that is the requirement, then the top surface will be there will be holes dig over the top surface, and with epoxy these shear connectors can be provided, and next concreting, new concreting can be done. This new concreting with this, because of the shear connection, will have proper monolithic connection with the old concrete, and thus the thickness or depth of the footing is enhanced. As we go on increasing the depth, so is less, so its bending resistance capacity and punching shear capacity is increasing, and that is how this kind of a retrofitting of footing can be done. If we require the other way, that it is the soil capacity poor, and hence I require as a part of retrofitting I require enlargement of the footing size. So naturally the task before me is whatever is this enlarged side must act monolithically with the old side. So for that, the shear connectors on this side is required to be placed, and these needs to be properly connected. In new concreting, when it will be done, this new reinforcement will act together with the reinforcement of this old footing, and thus the enlarged shape will come into action, giving safety to the footing system. Similarly, retrofitting of column, most of you must have seen about this kind of a retrofitting in many places, where this is the column and this is called as jacketing using steel sections. These are the angle sections. They are connected through welding plates like this. So this, in this system, column has its own capacity, and this new system, new angle, 4 angles on 4 sides, has its own capacity, and that is how total capacity of the whole this column is enhanced, because this is the new system added to the old system. This kind of a retrofitting is done. There is another way of retrofitting is with the steel bars and then concreting done. In this way, if it is done, the size is largely enlarged. Size is enlarged, and that is the negative point of this kind of a retrofitting, where this concrete column size is too large. It seems to be too large and not aesthetically appealing. The better part is this using the FRPC. This kind of wrapping is done using FRPC without enhancement in the size. Means old column size and new column size is almost same, bearing few millimeters change. So this kind of wrapping is done, then it is quite largely enhancing the capacity of the column. This kind of FRPC is done. Using FRPC at the bottom, the capacity of the beam can also be enhanced so far as bending resistance capacity is there. Similarly, these vertical wrapping enhances the shear capacity of the beam without changing the size of the beam. This is good point of it. Similarly, the slab also can be enhanced. The capacity of the slab can also be, as I said, that one residential building is converted to, say, a library building. Naturally, the library building will be subjected to more loads. To take that more load, I require more bending capacity. So this kind of a activity can be done with that old existing slab to enhance its capacity, and thus the retrofitting can be done. This is what is the system of slab FRPC. Here I am ending my this presentation. It is almost around 2 hours. So thank you very much for your patient hearing. I hope I am able to get you into the details of the seismic considerations and retrofitting techniques. Thank you very much for your patience.
Thank you, sir. You rightly focused on the topic and explained with great expertise. And thank you for this informative session. And now moving forward, I request all the participants to join the discussion, and they can raise their hands or can post their questions in WhatsApp group. So if there is any question, please ask.
Excuse me, I am architect R.M. Shambarkar, but Ramtekke sir has given a proper guidance because we are only referring the earthquake tips. But now, architectural point of view, sir, you have more elaborately has explained the considerations and retrofitting because the FRPC and its application, I was not aware. So thank you. The question is, what type of plan form and build form during the earthquake has been more safer as per the past earthquakes which has been generated? And because architectural point of view, I am asking any kind of plan form and build form to maintain the equilibrium of forces so that structure will be least damage.
Yeah. So basically, the symmetrical structure in plan, symmetrical just not by looking that it is symmetrical, but the distribution of masses means wall distribution of, because wall etc. these are actually causing the change in load system. If say one side I have given walls and other side it is just kept unwalled, then also the mass will be on that side. So there are things like that if the whole structure symmetrically planned with symmetrical distribution of masses will definitely give much better seismic behavior as compared to any other thing in that. So the plan symmetry is the most important. Then other thing is, as I said, because the confinement, so far as construction is concerned, confinement of reinforcement plays an important role. And it is the confinement of reinforcement at the location of beam column joint that becomes most important. Not only in the in between location. So at the beam column joint where there is congestion of reinforcement, somehow we should give the close spacing of the rings so that whatever concrete inside remain inside during an earthquake. One more thing, as there is congestion of reinforcement, from construction point of view I am saying it, as there is congestion of reinforcement, naturally it is difficult to vibrate the concrete. But somehow as an engineer or as an architect, we must take care that the proper vibration, needle vibration is put there so that concrete is dense and without voids there at that location. There it is prime important. So that is how it may give a better behavior during earthquake if it is done so.
And similarly, as in Bhuj earthquake, the Bhunga house or Bhunga hut, circular plan form and conical roof, that village has been saved, but the RCC frame structure has been collapsed. So I used to tell the students, whether it is right or wrong, I don't know, because I have not examined it structurally, but I said the circular plan form and what you can say, the roofing system means whatever the structural framework, it should be start from one end and another at another end, means like a hemisphere. So in that case, equilibrium of forces can be maintained. It is my analysis. It may be wrong. So I want to clear from you as a structural designer.
But the concentration of stresses can be avoided if it is a domical shape and circular shape of a building has a specific importance. If we have a rectangular or a square building, now as I said, the direction of earthquake is not known to anybody.
Yeah.
But a circular is a shape which is symmetrical in any direction.
Any direction.
Any direction, circular is the best direction, best shape. it is symmetrical under any condition. So that way the circular, and also because it doesn't have a corners, the concentration, stress concentration is not taking place. It is all
Yeah.
distributed there, and
Yeah.
that takes it away from any kind of a damages during a.
Thank you, sir. Thank you.
Thank you, sir. There is a question in the WhatsApp group, sir. In your view, how smart our ancient temple were, constructions were?
Ancient temple construction.
Yes, how smart they were.
Actually, most of the our ancient temples, if I consider, if they are symmetric, because we take it circular in shape and then there is a conical shape going up, that from that point of view it is good. But if in any other way it is like means, because most of the temples I have means come across in reading that from the stability point of view, a huge load is kept at the top of the top of the dome. From earthquake point of view, this is not good, but from stability due to gravity and construction system, क्योंकि उसमें जो है construction stone masonry was the construction way, and lime mortar was mostly used. Under that condition, उसको safe under gravity load, which is mostly coming is 24/7 into 365 days. Gravity load is coming from that viewpoint. Keeping the top heavy load at the top is good. From earthquake point of view, it is not good. That way I can say it like this.
Yes, thank you, sir. Any other question? So I don't see any other questions, sir. So we come to the end of the session. If there is any other query from participants, they can ask. We have at least 5 minutes more. Okay, thank you. I want to extend my generous thanks to expert of this session, Dr. G.D. Ramtekar. I want to thank him for his valuable time from his busy schedule to grace this occasion. And I want to thank him for sharing his graceful opinion with us. Thank you so much, sir.
Thank you very much. Thank you. So may I leave now?
Yes, sir, you can. Thank you so much, sir, for your time.
Okay.
Thank you, sir.
Thank you, Professor Ramtekar.
Thank you. Thank you very much, Ramtekar, sir.
He is already left, I think.
Yes, sir.
Okay.
So I also thank all the participants for their participation, and